Hello, folks. Welcome to the Cohere Labs Computer Vision Community uh, session, where we are talking about NeoBabel. Uh, so, as you might know, Cohere Labs is a hybrid research lab and an open research community that's dedicated to uh, contributing to the fundamental research in machine learning, working to solve some of the field's most challenging problems, and creating more points of entries into machine learning for the folks who are upcoming and who show interest in this field. Uh, Cohere's mission is changing how and by whom research is done. We have like open collaboration, fundamental research, training and development, and a huge community. We have 100 papers published, 60 plus collaborating institutions, and we have uh, got the fourth cohort that is ready for the research scholars from this year. Like we have 9 models that has been released, and 350K, more than 350K of API credits that has been distributed, and 4,500 members plus in our open science community. So we are a part of this guest speaker series here, but these are the community talks that you can find on the YouTube playlist, which is huge and quite interesting. And like as we have alluded to, we have the researchers from all around the world, and we have 12 subfield groups, 2 regional groups, and 3 professional groups that are there in total. And that's to have that. That's like the open science community has 17 active programs here, and a couple of sentences about Mohammad Mahdi Derakhshani. He is a PhD student at the University of Amsterdam's WIS lab, and he is working on his multi-modal foundation models with a focus on unified generative systems. Its research interests span scaling transformers, distributed data generation, decentralized distributed learning, and reinforcement learning with verifiable reports. He has also gained experience through research internships on large-scale language and vision models in Microsoft and others. And he is currently a community researcher at Cohere Labs, exploring multilingual generative model. So over to you, Mohammad.
Great. Let me share my screen with you.
Okay.
So, can you see my screen?
Yes, we can.
Okay. Let me start. Hello, everyone, and thank you for having me here one more time. Today, I'm excited to present NeoBabel, our multilingual open foundation models for visual generation. This is a joint work with Dirash. He's here, like I think in the chat. Marzia from Cohere, and Kees Snoep, my supervisor from University of Amsterdam. So before starting the presentation, I would like to ask you guys to feel free to interrupt me in case you need any clarification on my presentation. And yeah, let's start it. Let's begin with the motivation behind this project. We know that the current state-of-the-art AI model is predominantly monolingual, which means most models, especially in text-to-image generation, only support English prompts. This means that around 95% of the world's native speakers are left out, which creates a major digital divide. This is especially true for EU countries where only UK, if you consider it as a EU country, is English native, and the rest are not. So it left these questions like, what should we do with this huge amount of population that we have in the world, and especially in Europe? So to understand the gap better, let's actually look at the landscape of existing models. As we know, the field of image generation moves very, very fast. Most state-of-the-art image generation still operates only in English. And we have a few multilingual LLMs, but none are natively multilingual image generation models. Like, they're not natively trained for that, but we could see some multilingual image generation models, but like they are not natively multilingual. And more importantly, when it comes to openness, like in terms of data preparation, training scripts, like instruction tuning scripts and evaluation protocols, the picture is just limited, like making it hard for researchers in other regions to adopt or build on top of them. So how do we address this gap? We introduce NeoBabel, a multilingual, efficient, and fully open model. It supports 6 languages natively: English, Chinese, Dutch, French, Hindi, and Persian for now, while being up to four times smaller than existing models. And importantly, it matches like the current model that we have. It matches or exceeds like English performance model 2. Like in addition to be like pretty much very good models like in other languages. So let me summarize what makes like our NeoBabel unique. We provide 3 core contributions for the community. Like one, a natively multilingual text-to-image generation framework, which is obtained by building a large-scale, massive multilingual dataset and a unified multimodal architecture with a new progressive training approach. 2, a multilingual benchmark and metrics that we released together with the base code and the pre-trained model. And 3, like an open source toolkit to support inclusive research. I think that the last part is the most important part nowadays in generative AI, because like if you see the landscape, people usually release either their own weights or like fine-tuning training scripts. But when it comes to like data and pre-training and the receipts, they are not that much transparent. So like, since we wanted to be transparent as much as possible, we released everything regarding these 3 contributions like that we mainly introduced in the paper. And we hope that maybe it can like accelerate the process, like the research process in open source community. So let's start. Let's iterate over like the main contributions of our work. And the most important part is data. Because like multilingual image text data is where the challenge really starts, because we don't have such a multilingual data, or it's very hard to collect. So high quality image text pairs in multiple languages, as we know, are scarce. And we know that manual annotation is also expensive. So to address this, what we did is that we expand existing data set, which are actually proven to be effective for image generation tasks, according to like the literature of image generation modeling. And we translate them into their multilingual versions using model-generated recaptioning and translation pipeline. So we start from existing data set, and then we use existing AI model to first recaption them and then accurately, as much as possible, translate them. So the followings, as you can see in the tables, like are the data set that we considered. So we can like iterate over a few of them, like in more details. Here are some examples showing how we enrich existing data set. For example, ImageNet, we start from ImageNet labels and then translate them into 6 other languages. And for this, we use like very accurate models like Gemini experimental models, and like very good open source models like NLLB, No Language Left Behind by Meta. Or for example, for conceptual caption 12 million data set, what we did is that we recaptioned the images using like NeoBabel, the biggest open source models that we have access to, like I think 9 months ago. And then we use this, like the new caption generated by this model for the pre-training. So if I go back again one more time to this table, like I wanna mention something like very special. Like we didn't do the kind of captioning and translation for all the existing data set that you can see in this table. For some of them, we just did the recaptioning and we just use like the English, annotated data for pre-training. And for some of them, like we used like captioning plus translation. So like in further, like in following the slides, I would show you like how this like table would change after captioning and translation. So this is another data set, for example, for JourneyDB. First, what we did is that we start with NeoBabel and try to recaption images. And then when we have these very good recaption image, like recaption image, like captions, then we try to somehow translate them into 6 other languages, like using NLLB here, because like we wanted to use like the data set size is massive, like we have 4 million image and captions, and we wanted to translate them. So using like accurate models like NLLB, non-accurate models like ChatGPT or Gemini wasn't that much possible for us because it costs us a lot. So we decided to use like open source models, like the largest open source models like NLLB for doing the translation test. So after all of this pre-processing and I would say captioning and translation, we like expand the data set from 39 million image and captions to 124 million image and captions, like distinct image and captions. So as you can see here, for example, for data sets like ImageNet, we just use a translation pipeline. For conceptual caption and segment anything, data set, we just did the recaptioning. I explained to you why we did this. And then for the data set, like more fine-grained synthetic data, which proven to be very effective for image generation tasks, like Lion-Stick and JourneyDB, we use like recaptioning and translation. So yeah, that was the data part. So it was a very massive data pre-processing stage that we went through lots of data, lots of models, like to check the quality of which captioning model works best for us and which translation module works best for us. And we found this recipe that NeoBabel plus NLLB or Gemini experimental works best, like in our training setup. So now, with the data in place, when we know that the data is available, let's move to the model architecture, what kind of model we used. So NeoBabel is built around a decoder-only transformer backbone. So for this, we use Gemma 2 as an LLM, as the LLM backbone. So what we did is that for the text-to-image tasks, we first tokenized the text or the captions or the prompts that we wanted to feed into the model using Gemma 2 tokenizer. And accordingly, like for the image input, we also use. So let me again rephrase the problem setting. How it works? So we have an LLM. We have like a prompt highlighted as green here. And we have some masked, tokens, image tokens, like again, appended by the end of the text prompt. Given these two settings, like these two tokens appended, like concatenated together, we feed them through the NeoBabel architecture, which is Gemma 2 backbone. And what we do is that we try to like unmask the visual tokens that is getting masked like in the input. So that's how it works. So we have set of textual tokens and image tokens concatenated together, and we feed them through an LLM, and we ask LLM like to predict the masked visual tokens or image tokens. So so we need to tokenize like captions and image. And for tokenization, we use like for text tokenization, we use Gemma 2 tokenizer. And for image tokenization, we use MagVit-v2, like the visual tokenizer used also by other competitors like Show. As I said, the architecture is a Gemma 2, like Gemma 2 LLM decoder transformer. And the loss function, the kind of loss function that we are using here is discrete diffusion objective, which what it does is it tries to like predict the masked visual tokens. So that's how it works. And during inference, like we start with like a fully, masked image tokens. And what we do is that we iteratively call this NeoBabel architecture several times and tries to, gradually unmask some visual tokens until we reach to a full unmasked, let's say, image tokens. That's how like the training and inference pipeline works. It's like pretty much the idea of the masked LLM recently get hyped like in the literature, where we mask some textual tokens and try to predict them. So yeah, that's how like the NeoBabel multimodal architecture is designed. And let's see how did we train NeoBabel. So NeoBabel training actually is organized into 5 progressive stages across pre-training and instruction tuning. So stage 1 uses 6 million examples from multilingual ImageNet 1K to establish the basic so-called pixel level dependency in a multilingual settings, where we do not have like very long caption. We only have 1 or 2 or 3 words caption. And what we want like the model to do is to somehow try to understand how images look like in a very basic manner. So that's what we expect from stage 1, pre-training stage 1. Stage 2 actually scales the the data set size, scales alignment, like the like textual text image alignment with 94 million examples from multilingual segment anything and multilingual conceptual caption 12 million, and also multilingual Lion-istic. So what it does, it enables broad multilingual and visual generalizations by scaling up first the number of images that we are observing during pre-training, by increasing the complexity and diversity of the images, and also by increasing the number of languages and the density of the textual tokens that we are observing during pre-training. So stage 3 performs a refined kind of pre-training on 96 million curated samples from multilingual Lion-istic and multilingual GenDB. So like it's like continued pre-training. We wanted to give models we wanted to give models some access to high quality natural data, like Lion, which contains very good high quality natural data. And in the meantime, we wanted to give access like to some synthetic data generated by Midjourney. It's called generative. But both of them are high quality. So at this stage, model actually knows how how to generate like high quality data, but in a very low resolution way. So what we did is that in instruction tuning stage 1, we continue training from previous stage, but in a higher resolution. So we upsample the input image resolution from 256 by 256 into 512 by 512. So we also add a new instruction tuning dataset. It is called BLIP30 instruction tuning dataset into the data mixture that we use during instruction tuning to make it actually more aligned with the downstream tasks that we wanted to evaluate on. And in the second stage of the instruction tuning, again, we use like the same set of data mixture that we use in the stage 1. But like we changed the ratio of the data. Like in the first stage, we used more like Lion and JourneyDB and less, BLIP30 instruct. And in the second stage, we increased we changed this ratio by increasing the usage of BLIP30 instruct and decreasing the others. So that's how we train the model. Again, it's a unified model. It is able to generate, like right now, it is able to generate image, but with a potential of being able to generate text as well. And this is actually the way that we train the model on top of the existing data set.
I would like to ask, like, what was the sequence length for the phases, like the first stage, second stage, third stage? Did you change the LLM sequence length there, or like?
Yeah, I think for the first stage, we used like the sequence, like a context length of 128 textual tokens and 256 visual tokens, right? And for the later stage, we extended the textual token size and also the visual token size. So for example, I remember that from stage 2 and 3 of the pre-training, the number of visual tokens are fixed, like it's 256 visual tokens. But since we are using like recaptioned, we are using dense caption in the second stage and the third stage of the pre-training, we increase the number of textual tokens, like the context length belongs to the textual tokens up to 512 textual tokens. So the more we go, like we move toward the end of the training, we extend like the context length, because we are getting more high quality data and more dense textual tokens to describe the images. Is that clear?
Yeah, cool. And plus, like, what was the optimizer here? Adam W?
Everything is Adam, actually.
Okay.
Yes.
Cool. There were some queries in the chat, which I think so Dheeraj has answered. But if you would like to take a look at them.
But I wonder, why do we need causal attention for the text if it's always known during inference? Can we use the full attention? So regarding the question for the loss function, no, actually here we used, I think, the cross entropy loss function. I did training the model in the multilingual aspect doesn't impact the loss function choice here. And regarding the first question, why do we need causal attention for the text if it's always known during? So the thing is that like we had some, it's a very good question. So what was the main motivation of this project? At the beginning, we wanted to make a very a huge, like an open source unified model, which is able to generate image and text at the same time, right? For the text generation part, right, actually we needed like that causal attention, yes, we needed that causal attention. So for the current pipeline, sure, we do not need causal attention right now. But since we wanted to like kind of extend this architecture for more unified modeling in terms of being able to generate text in an autoregressive way, we needed that causal attention, design. I hope it's clear. Yes, that's for future project. Yes. Can I continue?
Yeah. So, just excuse me for a minute. I have a quick question for you, Mohammed.
Yes.
So at any point in the training, did you observe that perhaps some languages were more difficult to map from the text space into the image space? Like, for example, some languages have different structures, and perhaps the structures that they exhibit might make it difficult to map from their linguistic space into the image spaces. Did you observe any phenomenon that might
Yes,
suggest
we
that?
observe that like during these progressive pre-training stages, like we observe that we are getting different performance per language, which to some extent it makes sense, because like like some languages are underrepresented in the pre-training corpus, right? The LLM, the pre-trained LLM that we used, right? So it is kind of expected to see such a behavior in languages. Like it is
Okay.
expected to see some variations, like in metrics, when it comes to ablating across different languages.
Oh, okay. Yeah. So there's another question that I have. It's not so much a question, but maybe more like an idea that just dropped into my mind. So perhaps in a future iteration of this work, I think something that I would like to see is some kind of adversarial translation. So perhaps we get like two different models that can both translate from English to Persian, right? And then you use both of them to generate multiple different translations, and then you can try and use them for your training to see which one kind of performs better. If I'm making sense, if that makes sense.
Actually, I didn't understand actually what you mentioned here because of the quality of the voice. But I heard something like adversarial translation, something like this. Um,
Yes.
I don't know
Yeah.
what it is and how it can be helpful. But yeah, can you elaborate more on top of that?
Okay, so what I meant was say something like, let's say you use multiple different models. For example, you have two, three different models that can translate from English to French or from English to Persian, for example. And then you generate multiple different translations from each of them. And then you use these different translations to generate three different versions of the data set so that you can test which version of the data set gives you the best results, if that makes sense.
I still like missing your voice somehow. The quality of the voice is not that much perfect. So I'm missing like the last part that you are explaining. Maybe we can chat
Okay.
offline or text me something or text in the chat your question. Then
Yeah,
it,
Benedict,
Yeah,
please,
I will do that.
please put your query in the chat so that we can understand it. Plus, there was a query from Shamima regarding the infra that you used, and like you have open source the code, but if you would like to give us a detail about how you managed to train that in,
um,
yeah.
Um, so about the infra, we use several like clusters to train the model. So we use GCP like instance provided by Cohere Lab, right? Mostly for pre-training. And we had access to some European clusters, including Lumi, to be able to train our model on top of that. Like we use AMD GPUs, we use NVIDIA GPUs, like back and forth, like to train the, like to make the whole pipeline. So that's how, like that's what kind of infra we used. Like about the engineering pipeline, so for engineering pipeline, we mostly use Ray library, which enables you like to massively pre-process or post-process data in a distributed way. Like if you wanna like do something similar, I would highly recommend you like to use the Ray library. That's the thing I would recommend.
Cool, thanks.
So shall I continue or?
Yeah.
Okay.
Please do.
Okay, so now we talked about the data, we talked about like the training pipeline, the progressive pre-training approaches like that we introduced. Now it's time about like, it's a time about like evaluation. How do we evaluate such a multilingual data, like multilingual data? So that's another gap we identified. So we know that existing benchmarks like m-GenEval or DPG are English-centric or English only. So what we did is that we extended them into 6 languages. And so we introduced multilingual m-GenEval and multilingual DPG. So also we introduced 2 new metrics to test the crosslingual and code switching capabilities. So to test the crosslingual capability, we introduced crosslingual consistency score, which evaluates if a model can generate similar semantically related images given the same translated prompt. And for code switching capability, we introduced code switching similarity, where we evaluate if a model can understand mixed language prompts. I don't want to like to talk about these 2 metrics like in this presentation because it has a lot of detail. I would say I would recommend you guys like to check the paper, to check out the technical report that we wrote, and probably you can like ping me like in Cohere, you know, channel like if you have any further questions. But I would like to show you more like how we designed the m-GenEval and how easy it is like to like make dataset existing benchmark like image generation benchmark for multilingual tasks. For that, let's now zoom in one of these 2 benchmarks. Like so we start with m-GenEval. So m-GenEval actually it offers a kind of a structured evaluation of prompt to image generation to image alignment, focusing on 6 core compositional dimensions like single object, 2 objects, counting, colors, position, and color attributes. And for each prompt, which is paired also with some specific object and color requirement, we generate image. Like what we do in m-GenEval is that given a prompt, like from m-GenEval dataset, like benchmark, we generate an image. We then use something like object detection models to verify whether the expected objects are present in the image, correctly counted, and placed in the correct spatial arrangement. Like so, we use object detectors for this purpose. And then on top of that, like we use some discriminative models to assess actually fine-grained attributes like color. So what it does, what m-GenEval provide us, like it's a final score measure with whether all these elements described in the prompt are accurately depicted in the image. That's how it works. So what we did is that building on top of m-GenEval, we introduced multilingual m-GenEval, a multilingual extension of this benchmark. We take m-GenEval 6 object-focused evaluation tasks and translate them across 6 languages like English, Chinese, Dutch, French, Hindi, and of course Persian. And then after this, what we did is that we retain the rest of the m-GenEval evaluation pipelines and evaluate images similarly. So as you can see here in this image, we have some multilingual prompt using the multilingual image generation framework that we introduced here, like NeoBabel. We generate like image accordingly, and then after we generate the image, we use like the existing m-GenEval, let's say evaluation protocol to detect the objects, the locations, and color attributes. That's how we extended m-GenEval. And here we can see some results, like how our model works on m-GenEval. So we compare NeoBabel against the strongest available text-to-image baselines, models that either rely on multilingual LLM or a model that claim to be model that claims to have multilingual capabilities. So however, like when we look at across languages, a clear gap emerges. These baselines tend to perform well in English, but the performance drops sharply in non-English settings. And in contrast, NeoBabel actually delivers strongest and consistent results, highlighting actually the effectiveness of our natively multilingual training approach. So here are some examples from Dutch prompts. Like I study in Netherlands, in Amsterdam, so I preferred like to see like how it works when I prompt the model with Dutch languages. And it is working like on m-GenEval data. Like it supports, like it follows the prompt, the instructions, like for different tasks that like we evaluate the model on. So that was the way we extended the m-GenEval like benchmark to multilingual m-GenEval. Next, what we did is the same thing for a more naturalistic benchmark, which is called DPG. And this is how DPG works. So for each prompt sampled from a set of, let's say, 1,000 diverse prompts from a pool of prompts, we generate actually 4 images in a grid, like in a 2x by 2 by 2 images, and then pair these images with some natural language questions. So as you can see here, for example, like when we have the images, we start asking these questions like from the image, like, is there a parrot? Is there a sky? Does the parrot have a wingspan? Something like this. So, so we have some high-level question for each prompt. And what we do is that actually we leverage a VQA model here, which answers each question, and accordingly, like it's a binary answer, either yes or no, like because the questions is binary, like we can answer them by yes or no. And we filter out invalid and ambiguous responses, actually from the VQA model. And the final score actually will be a kind of average of valid question scores across all generated images. That's how DPG works. So what we did is that, again, similarly, we noticed that DPG can be easily extended to multilingual DPG if we just translate the prompts, right, accurately and properly. And for this, like, we did a very rigorous, human, translation. Like, we started with Gemini. We asked model, like, to translate each prompt properly, and then we check them one by one to be accurate as much as possible. And then what we did is that we kept pipeline for DPG fixed as it was, but we translate all these 1,000 prompts in 6 languages and generate again a kind of 2 by 2 grid of images. And then after that, everything is fixed. So that's how we went from DPG to m-DPG. And this is the results, again, for several languages that we evaluate on. NeoBabel, our architecture, performed best in multilingual setting, even though actually you can see that it's very much smaller than like the baseline, like the state-of-the-art baseline, like Blip 3.0, which got recently released, like I think 2 or 3 months ago. It is smaller, but it outperforms larger models like Janus Pro and Blip 3.0 in 5 non-English languages, while staying actually competitive in English dataset, like in English aspect. This is how it works. But actually, I would like to conclude the results section, like the numerical results section, with one another like very informative like figure we could find from our applications. So as I said, like our pipeline, our training is built on top of a kind of progressive pre-training and instruction tuning, stages. And as you can see here in this table, you can see the impact of like each stages. So we have 3 stages of progressive pre-training and 2 stages of progressive instruction tuning, and they are highlighted by different colors. So so as we go toward the end of the training stages, we incrementally evaluate our intermediate checkpoints on 2 benchmarks that we introduced, m-GenEval and m-DPG. And as you can see, like the first stage, it doesn't contribute too much in terms of these 2 benchmarks, like pixel dependency learning stage that we have. We trained the model on ImageNet datasets. And then the moment we start to integrate more high quality data, and more dense caption, the model gets like some improvement from the first stage, specifically for the m-DPG one. Like we shifted the performance from 10% to 65, around 65, which is huge, like for English dataset as well. And also we saw it in other languages. And then as we move like toward the end of the training, we can see that the performance gets improved. So that will be the impact, like the conclusion of how we should train like a model with more than 1 billion parameters, how we should babysit the architecture in a way that it start getting improved incrementally by adding more data and playing, let's say, with the quality of the data, with the resolution of the images. Like this is like one of the greatest lessons that we could obtain from this experimentation on top of this NeoBabel architecture. So let's talk about application, like how NeoBabel works here, like what kind of application it can provide for us. So it supports applications like multilingual in painting, when users can actually modify an image using prompts in any supported languages. So actually this makes creative control accessible to more users actually. So what it can I assume that like it breaks the barrier between different people in different parts of the world. For example, the input image, like in this figure, can be generated by a Dutch person, like in a Dutch language. And like the output image here, like the edited image, can be generated like by a person lives in India or in China. Like it increases the interaction, and it breaks the barrier such that like nobody, like people can talk in their own language, right? Other than, I mean, instead of learning like one unique language, which is English, in order to be able to communicate together. That's one of the nicest things we observed from actually from our architecture, which is able to do multilingual in painting. It also can do like multilingual out painting or extrapolation, which means that you can start from one image and try to extrapolate or extend an image horizontally and vertically in different languages. So that's one of the applications that we found that it can be interesting for the community. And another one, I think, which is kind of more interesting, is that NeoBabel is capable of handling code switching. So probably for those of you who are unfamiliar with this term, code switching refers to prompts that mixes multiple languages or scripts to express a single coherent concept. So let's see how it works. So let's assume that this is the English prompts that we have. Like, what does it have? Like it has like probably 3 sentences, like the first sentence, the second sentence, and the third one, right? So what we did, we run an ablation to see what will happen if we just use the first sentence as English, translate the second sentence into Dutch, and the last sentence like as French, and then concatenate them together and send them to the NeoBabel architecture and see what actually model generates. And surprisingly, the model could generate very good coherent images given the mixed prompt that we gave to the model, right? and it's kind of robust. So actually, this is kind of, behavior that we as a human, like actually multilingual human, expect from, let's say, giant models, from like closed source models like ChatGPT or like Gemini. So for example, assume that you're playing with ChatGPT, and at the beginning you're just doing some coding with it, like trying to prompt ChatGPT to generate some code for you. And suddenly, like in the chat, you switch from, let's say, English language to another language, your native language. And what you expect from the model is that it doesn't like behave, behave abnormally, like in an inconvenient way, like starting hallucinating just by changing the language. So this is a kind of expectation people expect from like models that has code switching behavior. We also did this ablation on our NeoBabel architecture, and we found that it supports code switching. So, and also I wanted to highlight this fact that we haven't actually trained our architecture, our NeoBabel architecture, in a code switched way, meaning that during like each stage, like each iteration, we just like sample a few language, like one language, a prompt is provided in one language, and we just train like the model to be able to generate an image, right, given that language. So there is not any instance in data batch which is designed in a very code switched way. So the model is trained in a very normal way, and after that, like we saw this code switching behavior from the model, which is kind of surprising for us. We haven't explored actually why this is happening. Probably the backbone LLM that we are using, like Gemma2, it has this functionality, and that functionality kind of transferred to the image generation task that we are trying to do. And we assume that this area of the image generation, code switched image generation, haven't been explored yet, and we leave it like as a kind of open question for the community to dig into it more, like to see what is happening actually there. And the last part.
Just a quick query here. So like you also have like in the paper you have described the visual similarity kind of equations that give the code switching similarity index kind of,
Yes.
and they are like the two parts, if I am right. One is the English first, and second is the English second.
Yes.
So yeah, so there I think so. You have the visual similarity between the image generated from the pure English and from the mixed English with other supported languages. So was this metric used in the code switching? So I would like to ask is how
Yes.
was this metric used? Yeah.
So actually, that's so we wanted to like introduce a kind of numerical value, right,
Okay.
for this code switch like analysis. So what we did is that we started from like a few prompts, right, which has at least like 2 sentences in it, and then what we did is that we divide the prompt into 2 sections, right, 2 splits. So what we did is that we keep the first split as it is and try to translate the second like a split like into other languages, right? So that's a new prompt. So we give that prompt to the model and we generate an image, right? We also have the original prompt, which is purely English. For that prompt, right, we also generate an image. So when we say the model has code switching, behavior, it means that the 2 final images, right, semantically and structurally should be similar to each other, right, when we code switch the prompts, right? So for doing that, we introduce like that matrix, right, to measure this for us. So we use 2 backbones. We use clip backbone, right, to measure the semantic, and we use the dyno backbone to measure the structure of the image, the layout, the texture, all of this stuff that we are interested in. And it means that the higher this score gets, right, the more code switch behavior actually the model has. So I said, like, regarding like the The scores, like all of the metrics that we introduced, it's a lot, like it's a technical report. I didn't have time to elaborate on them here, like in this presentation. But yeah, like if people are interested, like to explore like this behavior, probably do those two metrics that we introduced, that would be very good starting point for the community to understand like this phenomenon better. I hope I answered your question.
Yeah, thanks.
So I think there are a few questions in the chat. Do you have any other interesting observation in the generated images because of the multilinguality? So actually, we noticed something very weird, which was at the beginning, we were thinking that if we train our model on top of multilingual data, we could get some cultural, aspect of a country or a language, right, when generating an image. Let me tell you like one example. So when you prompt the model to generate like a historical place in Persian, right, or historical like a photo of a monument written in Hindi, right? What do you expect from the model? Should it generate something from United States or United Kingdom, or it should generate something from India? Like, I mean, some localized images. Like, to me as a researcher, I would prefer to see something for that specific country if the prompt, right, is provided in a local languages. We, like at the beginning, we had this idea that maybe this kind of cultural biases that we expect, we can get them after multilingual, pre-training and instruction tuning. But after training, we noticed that it is not actually happening, right? And we also noticed that these giant big image generation models like Gemini, Banana, like Imagen and ChatGPT, they also do not support like this kind of behavior, like local global behavior, right? So this is a kind of observation we also found from our ablation and experimentation, that the current model lacks this behavior, which is kind of good, because as a person who lives in like Iran, as a person who doesn't know anything in English, when I want to play them with the model to to generate an image, I expect to see something from my country, right? Not from other countries or some random countries. So this behavior is missing, like from the current NeoBabel model. We are trying to like extend this capability into the next version of the NeoBabel. But I'm saying constantly that this property, which is a very nice property, is missing in giant models, and people can like dig into it more to understand it, like why this is not happening. So that would be another observation that I would like to share with you regarding our experimentation and ablations. So if there is not any question, I can continue with my presentation.
Yep, you can.
About being open and also inclusive. So we decided to be transparent as much as possible. So we released the paper, the technical report, we released the code bases, like completely from the data, from downloading the data, pre-training data, instruction tuning data, like to pre-training script and instruction tuning script. And also we released the full evaluation protocols. We released the pre-training data, instruction tuning, and also evaluation data, but we haven't released the models because we wanted to check that the model is super safe in terms of generating the content. So we are trying to post-train it a little bit more, like to be able to not generate toxic, let's say, images. We will release it soon by the end of the probably September, because right now we are pushing for submission on top of this paper. So for people like probably Cohere Lab communities, if they want to build something for multilingual, I think image generation, probably this base code that we are releasing, it's a very good starting point for everyone, because it supports so many things. So it can be scale up like to 1 node, 2 node, 3 nodes, 6 nodes, whatever number of nodes that you want to do. Like it supports web data set kind of data loading, in a sense that you can load your data in a very streaming way without being worried about like the file system. So it supports so many existing techniques, like using accelerate and deep speed, like 0-2 kind of, you know, model sharding to be able to train the model like on small GPUs, like, or large GPUs. Like this, the base code that we released, it's comprehensive, and it's going to be a very good starting point for everybody who are interested to work or doing research on top of visual generation in a multilingual way. Please visit our website, like, to know more. Please let us know if you have any question. And please give us a star on our GitHub repository if you think that this is actually a good like foundation for doing research in an inclusive way. And let's conclude. To wrap up, NeoBabel actually proves that in a high level, multilingualism is a catalyst. It's not a trade-off. And our architecture is performant while being smaller and more inclusive, you know, including more people from different countries. NeoBabel actually provides a curated data set, a novel architecture, a progressive training strategy, and a rigorous evaluation framework. And lastly, we are releasing a fully open toolkit to democratize research, including checkpoints, multilingual dataset, training scripts, and multilingual evaluation suite. And this is the acknowledgement part. I would like to thank Cohere Labs for especially from Marzieh, for valuable feedback, and also giving us you know, generous compute resources for conducting and analyzing our experiments, and some other you know European people who gives us some access, like NWO, Lumi, Euro HPC, and you know, Snellius in Netherlands. And by the end, also would like to appreciate my supervisor, Kies Snook, who helps us to finish these projects. And I think that's it, the end of my presentation. I would be happy to answer any question if there are.
I honestly don't think there are any questions at the moment. I think you answered most of the questions that we had. But I will throw it open to the chat. I will throw it open to the folks on the call. If you have any questions, please, Mohammed is more than happy to answer
Yes.
your question.
Yes, like me and Diraj, we are part of Cohere Labs, you know, community. So we are there
Nice.
in the Discord channel. So please feel free to ping
Nice.
us if you want to collaborate, or if you want to extend this idea, like into, like, if you want to explore this idea in different aspect of multilingualism.
Yep. Mohammed, what is your Discord username?
I do not remember. I need to check it out. Just
Dheeraj is Cold Coffee 2021, I suppose. Yeah.
Yes, that's correct.
I don't think I've ever actually messaged Viraj, but then again, maybe that's just me. So I'm also quite bad with remembering usernames. I don't really know the usernames of people I interact with frequently.
yes.
Mhm.
So actually, my
So
username is meme shiny. I type in the chat. So
okay.
Cool.
Nice.
Other than that, what are your thoughts for the multilingual model merging? I think so. There was a section in the paper regarding that too.
yes, the model merging part. So so actually, let me remember exactly what was that part, because it was a very long time ago. So what we did is that so we thought that if we so it was a kind of progressive pre-training approach, right? So we noticed that in the second or the third stage of the pre-training, we are reaching to a very good performant model, which can behave pretty much good on tasks like DPG, right? Which is a kind of more natural prompts compared to like whatever GenEval is evaluating, right? And we noticed that when we train more, like the performance of the, the performance of the model on DPG benchmark decreases, right? While the other performance regarding the GenEval, like m-GenEval, is keeping it keeps increasing. So we noticed that like we need to somehow preserve, right, the basic performance that we could get at the end of the stage 3. So what we said is that, okay, let's assume that we are doing instruction tuning 1, and we are training the model for 500,000 iteration. And we said that, okay, let's get let's store some intermediate checkpoints, right, during during instruction tuning, and let's try to somehow linearly average them, right? Take the average of these like intermediate checkpoints, with the hope that by doing this kind of averaging, we are not actually forgetting the original performance that we could get by the end of the pre-training stage 3 for DPG benchmark, right? So that was the main reason we did the merging part. And surprisingly, it works. Like it tries to like at least increase the performance by 1 or 2% on DPG, right? So that was the main reason we did it. And we know, like we also know from the other papers from the literature, that people are doing the same thing for LLM and VLMs, right? The paper by, I don't know, ByteDance, they also did this kind of ablation to see like what would be the impact of model merging, like basically from the beginning of the pre-training. And it showed that it is working, and it provides a very good generalization across a wide, a wide range of downstream tasks. So we saw the same observation, and I think honestly the main motivation for us was to keep the performance of the DPG, right? And that's the reason why we did it.
Cool. So like in the resulting model that you provided, the 2 billion one, so did you did you do the model merging there too?
We did a model merging in the first stage and the second stage of the instruction tuning.
Okay, nice. Thanks. Do you guys have any more queries? I think so. Query by Shamima was any suggestions or pointers to fine tuning on her native language, that is Bengali.
So the first thing, you need to get the data actually, and the next thing is that you need to wait for us to release our model, the Hindi, the backbone which supports Hindi, and probably you can fine tune a little bit our model on top of your the collected data set to be able to generate something in your native language, Bengali. I think that would be suggestion.
Yeah. So and that was actually a very nice presentation. Another idea I just had is what do you think about experimenting with languages that have similar etymological roots? So, for example, languages that evolved out of similar regions, or languages that evolved out of similar parent languages, if that makes sense. I have similar linguistic roots. So perhaps we could experiment with NeoBabel, train multiple NeoBabel models on different languages from different linguistic groups, and then do some model recycling or model merging to see if we can combine all these capabilities into one mega model, if that makes sense.
Yeah, that's a very nice idea, to explore. So for example, we were thinking that if we are training on top of Persian, probably we can do the same thing on some Arabic, prompts, because they have the same alphabet, something like this. But we didn't see like any, nice behavior when we prompt the model on Arabic prompts. It seems that like to get a very good model, like to get a very, very performant model, you need to collect a lot of data in different variations, in different diversities. From different region, and try to train the whole, like one model on top of all of them, or try to different distinct model per language, and then after that doing model merging on top of them, like merging different models trained on different languages. So to be honest, we haven't explored too much like what can be done with this architecture, but I'm quite sure that like there are so many open problems there, like in terms of model merging, similar languages. So there was actually a group of people from Stanford. They reached out to us. They were asking about something like underrepresented group, like which like some specific languages that doesn't have proper representation in terms of data sets. So there is a lot, like people can do so many things based on the recipe that we are selling to the communities. So I would say there is a lot, and we just started. And since we didn't have too much like energy to continue, we just decided to leave the base code as open source and let other people to work. So oh yeah, that would be my comments regarding your question, if I answer your question properly.